Have you ever been sitting at your desk at, say, 2 in the morning, just staring at your screen,
Oh, absolutely.
locked in this absolute battle of wills with your AI coding assistant? I'm your host, ready to jump into our deep dive today.
And I'm your resident expert, and I know exactly the feeling you're talking about.
Right, because you ask it to help you refactor a messy component, and sure, it spits out a decent single function, but then you ask it to integrate that function into the rest of your app, and it just completely loses the plot.
Completely.
It hallucinates a library you deleted 3 days ago, or it overwrites a crucial piece of business logic. It literally just helped you write an hour prior.
Which is incredibly frustrating.
It is. You find yourself wishing it didn't just act like an overeager intern who needs constant supervision. You're wishing it could act like an entire software development agency, an agency that manages itself, proactively tests its own work, and actually remembers the mistakes it made yesterday.
If you are nodding your head right now, you are in the exact right place.
Welcome to the deep dive. We've got a really exciting mission today.
We do. We are unpacking a massive stack of documentation from an open-source GitHub repository for a platform called Ruflo.
Specifically, we're looking at their new version 3.5 release, right?
Exactly. Our goal today is to explore how this platform takes it, Claude, which we already know is a very powerful underlying model, and transforms it from a solitary single chat assistant into a self-learning multi-agent enterprise swarm.
Which, it sounds like science fiction, but looking through the source material, this is a very clear, highly functional glimpse into the near future of software development.
It really is a massive paradigm shift in how you, the listener, are going to interact with code moving forward.
Yeah, we are just talking about a better autocomplete here. We are talking about a completely different architecture.
Yeah.
So let's jump straight into the first major concept from the repository, which they call the Hive Mind.
The Hive Mind.
Yeah. The documentation details that Ruflo deploys not just one AI, but a coordinated ecosystem of over 60 specialized agents. Over 60. Instead of having one general AI trying to context switch between writing CSS, configuring databases, and then, writing unit tests, Ruflo uses highly specialized roles. You have a dedicated coder, a tester, a security architect, a reviewer, an optimizer.
And it just keeps going.
It does. Let's unpack this, because my immediate thought is that throwing 60 AI agents into a single project sounds like a recipe for absolute chaos.
Oh, totally.
If they aren't structured perfectly, aren't they just going to talk in circles?
Which is exactly what happens in older, more naive multi-agent setups. But to manage a swarm of this scale, Ruflo relies on a hierarchical command structure driven by what they term queen agents.
Okay, queen agents.
Yeah, you can think of this as having a highly disciplined digital management team orchestrating your specialized developers. There are 3 distinct types of queens. First, the strategic queen handles high-level objective coordination.
So if I drop a massive feature request into the prompt...
The strategic queen is doing the research. It's breaking down the epic into tickets, planning the architecture.
Okay, so it's essentially the product manager mapping out the sprint.
Precisely. And below that, you have the tactical queen. This agent is down in the trenches, assigning specific files and tasks to the specialized worker agents, like telling the coder agent to build the database schema, while simultaneously telling the tester agent to prep the unit tests.
Got it. And the third queen?
The adaptive queen. That one serves as a real-time monitor. If the tester agent keeps throwing errors because the coder agent's logic is flawed, the adaptive queen dynamically adjusts the strategy. It might pull in a reviewer agent to break the deadlock.
I see the structure, but I'll be honest, I'm still a little skeptical.
Fair enough.
Because even with a management hierarchy, we know large language models hallucinate. I've tried putting AI agents in feedback loops before, and sometimes one of them just completely derails the process.
Yeah, one bad apple.
Right. What happens when the coder agent confidently hallucinates an NPM package that doesn't even exist? Doesn't the whole swarm just adopt that bad information and crash the project?
What's fascinating here is how Ruflo mathematically prevents that exact scenario using distributed agreement protocols.
Okay.
Specifically, they implemented the Byzantine fault tolerance consensus algorithm.
Wait, Byzantine fault tolerance? I usually hear about that in the context of blockchain, right? Or distributed server networks, like preventing a corrupted server from taking down a whole cluster. What is it doing inside an AI coding tool?
It serves a very similar purpose. In a swarm environment, you have to operate under the assumption that at some point, an agent will fail, hallucinate, or just write terrible code.
Sure.
The Byzantine consensus algorithm requires a 2/3 supermajority for the swarm to make any critical architectural decision or commit. The agents actually evaluate and vote on the proposed solutions.
Wait, so if the tactical queen assigns a complex logic problem, it doesn't just trust the first coder agent that finishes?
It doesn't. Multiple specialized agents might review the output or attempt the task in parallel. Yeah. For the code to be accepted, 2/3 of the participating agents must mathematically agree that the output is sound, secure, and meets the requirements.
So the swarm is mathematically fault-tolerant.
Exactly. Even if up to a full third of your agents are acting faulty, hallucinating, or failing completely, the swarm as a whole will self-correct. It effectively crowdsources the truth among the AI agents. You, the human developer, don't have to manually step in and referee a dispute every time an agent makes a logical leap.
That completely changes the dynamic. The AI agents are peer reviewing and voting on each other's work to filter out the hallucinations.
It's a game changer.
That alone is a massive leap forward. But it leads us directly into the second major hurdle of working with AI, which every developer listening knows intimately.
AI amnesia.
Exactly. The dreaded context cliff.
It is the single biggest bottleneck in modern AI development.
Let's break down why that happens for a second. Models like Claude have a token limit, a maximum memory capacity, which is currently around 200,000 tokens for the larger models. When you are working on a massive enterprise code base, loading in multiple files, documentation, and long chat histories, you hit that ceiling fast.
Very fast.
And when the AI reaches maximum capacity, it is forced to compact the data. It essentially summarizes the older parts of your conversation to make room for new prompts. And when it summarizes, it drops the exact details.
It forgets precise file paths, it drops the outputs of terminal commands.
And worst of all, it loses the step-by-step reasoning of why it made a certain architectural decision 2 hours ago. It's like your pair programming buddy just suffered a factory reset mid-sprint.
It completely breaks your flow state. You end up spending half your day just reminding the AI about the rules of your own code base.
Yeah.
Or repasting the same error logs.
Here's where it gets really interesting, though. The documentation outlines a feature called the context autopilot, designed specifically to kill this problem.
Yeah.
Instead of letting the model helplessly hit that context cliff and drop your data, Ruflo actively monitors the context window. The moment it starts getting too full, Ruflo intercepts the compaction phase.
Proactively.
Right. It proactively archives those conversation turns, the exact file paths, the reasoning steps, the specific code snippets, and it stores them in a custom format called RVF, which stands for Revector format.
And the engineering behind that RVF format is a critical piece of the puzzle. In older iterations of this software, the developers relied on a WebAssembly database dependency.
Right, WASM.
For those unfamiliar, WebAssembly, or WASM, is a way to run high-performance code in a web or node environment. But in this case, it was an 18-megabyte blob.
That's huge for a local tool.
It was heavy. It caused slow load times, and it created major compatibility issues depending on the hardware the developer was using.
Yeah, nobody wants their local development environment bloated by a massive database just to run their AI assistant.
Precisely. By stripping out that heavy WebAssembly dependency and building this pure TypeScript RVF format from scratch, they achieved something remarkable. They dropped the cold start times of the application from 2 full seconds down to under 50 milliseconds.
50 milliseconds. That is virtually instant.
It is. It runs natively everywhere without needing complex background compilations, and it gives the swarm instant, searchable access to every decision it has ever made on your project.
Okay, so it's incredibly fast, and it solves the amnesia problem by instantly retrieving those archived logs. But I want to push on this a bit.
Sure.
Archiving text logs and making them searchable is basically just a fancy local search engine. It's not actual learning. How does the swarm use this data to actually get smarter over time, rather than just rereading its old notes?
This is where we transition from a simple tool to a neural architecture. Ruflo utilizes a system called SONA, or Self-Optimizing Neural Architecture.
SONA.
Right. The platform isn't just statically saving code blocks. It is actively recording the execution path of an action, observing the terminal output, and judging whether the outcome was a success or a failure.
Meaning it runs the code, sees if it passes the test suite or throws an error, and logs that result.
Yes, and then it learns from that trajectory using 9 built-in reinforcement learning algorithms.
9 of them.
Yeah, the documentation lists several, including proximal policy optimization, or PPO, and Q-learning. But if we strip away the dense machine learning jargon, you can think of this process like training a dog.
Okay, I like that analogy.
When the AI agent writes a block of code that compiles perfectly, passes the unit tests, and meets the objective, the system rewards that internal pathway. When it writes code that throws a syntax error, it penalizes that pathway.
So it's reinforcing the good behavior.
Exactly. Over time, the swarm naturally gravitates toward the patterns, architectural styles, and specific quirks that work best for your unique code base. It is constantly training itself in the background.
So every time I ask it to fix a bug, it's grading itself and updating its own internal logic.
Yes.
But wait, if it's constantly adjusting its internal weights and learning new things based on my daily tasks, doesn't it run the risk of overriding older, successful behaviors?
Yeah.
Like, if I have it working entirely on front-end React components for a month, is it going to forget how it perfectly optimized my Postgres database queries 3 months ago?
You've just described a massive vulnerability in machine learning known as catastrophic forgetting.
Catastrophic forgetting.
Yes. It is incredibly common for neural networks to acquire new skills at the expense of old ones. But the Ruflo team accounted for this by implementing a mechanism called EWC++A, which stands for Elastic Weight Consolidation.
EWC++ a day. That sounds dense. How does that actually work in practice?
You can think of EWC++ as a mathematical protective layer over the AI's memory. When the neural architecture updates its internal weights to learn a brand new coding trick, EWC++ identifies which specific neural pathways are crucial to previously successful patterns.
Whoa, I see.
It then essentially puts a do not overwrite lock on those specific pathways. It allows the AI to stretch and adapt to new information, but it mathematically penalizes any changes that would damage the core knowledge it has already mastered.
So it guarantees that the AI can acquire new, highly specific skills for your front-end work without accidentally destroying the successful database strategies it learned months ago.
Exactly. It's building a permanent, compounding knowledge base.
That is fascinating. Okay, so we've established we have a fault-tolerant swarm of 60 agents. They have perfect recall, and they are constantly learning without overwriting their own brains. Let's pivot to something highly practical that every listener is going to immediately care about.
Speed and cost.
Exactly. Because running 60 advanced AI models simultaneously, polling an API every few seconds, sounds like a fast track to bankrupting an engineering department. My AWS and API bills would just melt my credit card.
Oh yeah, it sounds wildly expensive.
Yet the documentation claims Ruflo extends your Claude Max usage limits by 2.5 times and reduces direct API costs by up to 75%. How is that mathematically possible?
This raises an important question. Why would you spin up an incredibly expensive, slow supercomputer to do simple middle school math?
You wouldn't.
Right. But that is effectively what developers are doing today when they ask a massive, top-tier, large language model like Claude Opus to perform a basic mechanical code edit.
Right.
Something like changing a variable name across 3 files or adding a generic try-catch block.
It's overkill.
It is a massive waste of resources, time, and API tokens. Ruflo solves this through an intelligent 3-tier routing system. It analyzes every single task before executing it and automatically routes it to the absolute cheapest, fastest handler capable of doing the job.
Let's walk through a real-world scenario with those 3 tiers. Say I'm working on an app and I just want to add standard console error logging to 50 different files. I don't need complex logic. It's just a repetitive chore. How does Tier 1 handle that?
Tier 1 is called the Agent Booster, and it is built precisely for those mechanical edits. Things like converting a var to a const, adding TypeScript type annotations, or inserting standard logging.
Okay.
For these tasks, the router bypasses the LLM entirely, doesn't use AI at all. Instead, it routes the task directly to a local WebAssembly module.
So it's executing a deterministic script locally on my machine. What does that cost?
$0.
Wow.
And the speed is under 1 millisecond. The documentation benchmarks this as 352 times faster than sending that same prompt to a large language model and waiting for it to generate the text response.
That is an incredible optimization. So what happens if I need something a bit more complex? Say I need to write a standard user authentication endpoint, or I have a bug in my payment gateway that needs a standard refactor.
That falls to Tier 2. The router identifies the task as medium complexity and sends it to faster, significantly cheaper AI models like Claude Haiku or Sonnet. These models are highly capable for standard coding tasks. They take about half a second to 2 seconds to respond, and they cost fractions of a penny compared to the massive flagship models.
And finally, Tier 3. If the task requires deep reasoning, say I'm asking the swarm to architect a distributed microservices backend from scratch, or perform a massive system-wide security overhaul.
Only then does the router spin up the heavy artillery. It sends that task to Claude Office. That will take 2 to 5 seconds and is the most expensive option. But because the system filtered out all the boilerplate and mechanical edits in tiers 1 and 2, your Opus API calls are reserved strictly for the heavy lifting.
For you, the listener, you have to look at this not just as a coding tool, but as an automatic optimization engine running invisibly in the background. It is managing the logistics of efficiency so you never waste your subscription limits on syntax cleanup.
Exactly.
But as we scale up this efficiency and we have dozens of agents working simultaneously at lightning speed, my mind immediately goes to the codebase itself.
The merge conflicts.
Yes. Anyone who has ever worked on a team with even 3 human developers knows the visceral pain of merge conflicts. Now imagine 60 AIs touching the same files at the exact same moment. It sounds like pure, unadulterated spaghetti code waiting to happen. How does Ruflo prevent the repository from collapsing in on itself?
Traditional version control systems like standard Git use locking mechanisms that simply weren't designed for the speed and concurrency of AI agents. To prevent that chaos, Ruflo engineered a completely custom self-learning version control system called Agentic Jujitsu.
Agentic Jujitsu, I love the name, but how is it better than Git for multi-agent coordination?
It abandons the traditional file locking bottlenecks. The benchmarks in the repository show that for concurrent commits, meaning multiple AI agents writing to the repository at the exact same microsecond, Agentic Jujitsu is 23 times faster than standard Git.
That's huge.
But speed isn't even its best feature. Because it is tied directly into that RVF memory architecture we discussed, the version control system actually understands the semantic context of the code changes.
What do you mean?
If 2 agents edit the same function, Agentic Jujitsu doesn't just throw a generic merge conflict error. It understands the intent of both changes and automatically resolves 87% of those conflicts without requiring any human intervention.
A version control system that actually understands the business logic of the code it's managing. That is wild.
It is.
But preventing merge conflicts is really only half the battle. How do you prevent the swarm from drifting away from your original prompt? If I tell the swarm to build a simple login page, how do I know the security agent and the database agent aren't going to go off on a tangent and start rebuilding my entire user schema from the ground up?
That is a critical concern.
Yeah.
And Ruflo handles it through a methodology called Spec-driven development. Before a single line of code is written by the swarm, the queen agents are required to generate ADRs, which stand for Architecture Decision Records.
ADRs.
They effectively write up a rigorous specification document defining the exact boundaries of the task, the required endpoints, and the expected outcomes.
If we connect this to the bigger picture, the AI is essentially taking over the role of a systems architect. It's forcing a strict measure twice, cut once philosophy on itself. It has to state its assumptions and boundaries before it is allowed to touch your code.
And to give the human developer complete transparency into this process, Ruflo provides a real-time status line directly in your terminal. As the swarm works, this status line provides live metrics. It tracks the progress of the domain implementation, monitors the memory usage of the RVF format, and crucially, it performs live CVE scanning.
For those who might not be deep into cybersecurity, CVE stands for Common Vulnerabilities and Exposures. It's basically a master list of known security holes. So as the AI is writing code, this status line is acting like a bouncer at the door, checking every line against known exploits to ensure the agents aren't accidentally introducing a vulnerability.
It gives you peace of mind while the swarm operates autonomously. And perhaps the most practical aspect of all this is the integration. You don't have to drastically change your workflow or learn a completely new proprietary code editor to use this. Ruflo utilizes MCP, the Model Context Protocol,
which is essentially a universal translator cable that allows Claude to talk directly to your local file system and your existing development tools.
Exactly. Through MCP, Ruflo acts as a local server that plugs right into VS Code, Cursor, Windsurf, or the Claude desktop app. You just do a few configuration steps, and you bring this entire enterprise-grade orchestration platform directly into the environment where you already feel comfortable. It lowers the barrier to entry significantly.
So what does this all mean? When you take a step back and look at the aggregate of these systems, the Byzantine consensus algorithms validating the code, the context autopilot preventing amnesia, the EWC++ protecting its long-term memory, the intelligent 3-tier routing saving you money, and agentic jujitsu managing the concurrent commits, it represents a massive fundamental shift in our industry.
It really does.
We are moving away from the era of AI as an autocomplete tool. We are entering the era of AI as an autonomous engineering department. Your role as the developer is fundamentally upgrading. You are shifting from simply typing out syntax to being the director who orchestrates a highly efficient, self-learning digital workforce. You set the vision, define the boundaries, and the swarm executes the labor.
It is an incredibly empowering shift, allowing single developers to build at the scale of entire teams. But as you noted, it fundamentally changes the day-to-day nature of the job.
It really does. Which leaves us with a fascinating and maybe slightly provocative thought to end on for you, the listener. Think about the trajectory we've just mapped out. If AI swarms can now independently form mathematical consensus on architectural decisions, if they can peer review each other's code for security flaws in real time, and if they can permanently learn from their mistakes using advanced neural architectures without any human intervention whatsoever, at what point does the human developer's role shift entirely from creator to simply auditor?
That's the real question.
And if the swarm is mathematically, programmatically smarter, faster, and more fault-tolerant than we are who audits the auditors, something to mull over the next time you open up your code editor and stare at a blank file. Thanks for joining us on this deep dive into Ruflo, and we will catch you on the next one.